Wonderful. Well, thank you very much, and welcome everyone. We've got some people online too, it's my great pleasure to welcome Professor Masahiro Yamashita, who's visiting us from Japan. So thank you very much for visiting us for this LCN seminar. So Masahiro is just an incredible scientist in the area of molecular magnetism and materials for quantum. He's currently based in Tohoku in Sendai, but where he is enjoying his retirement by being more prolific than ever. And enjoying a lot of European travel as well, and visiting various research groups also at UCL and other places around the UK and Europe. He's got also a position in China with links in Shanghai. And as you will have seen from his CV, he's got many awards and distinctions. Award of Fellow of the Royal Society of Chemistry, Award of Japan Society of Coordination Chemistry, etc., etc. He's organizing one conference a year. I attended one on the International Conference on Coordination Chemistry, which had 2,500 attendees, and was really great fun. And I think you have seen many publications, including review articles going up to 650, and I think there is an ambition to get to 1,000 within the next decade or so. So we really look forward to hearing from Masahiro on new quantum molecular spintronics, and it's available online, and hopefully everyone's okay to be recorded, so there'll be time for questions afterwards. And thank you very much for visiting, and the floor is yours.
So thank you for some kind introduction. So today, which do you want? Here? Both? Okay, I use this one. Okay. So today my talk is molecular spin tube for quantum computer and high density memory devices based on molecular magnets. So, and actually, I stay in London more than 30 years ago for 1 year. I was visiting professor of University of London. At that time, my supervisor was Professor Robin Clark. 2 years ago, possibly. So, anyway, I stayed for 1 year in London. I enjoyed very much, not for science, not for food, but for sightseeing. I enjoy very much. Anyway, so so last year, Nobel Prize in Physics is experimental evidence of quantum entanglement. So very nice work. So this quantum entanglement is strongly correlated to the quantum computer. So today my talk is first, I focus on the quantum computer, and second, high density memory devices. First, for the quantum computer, I focus on the molecular spin qubits and the coherence even at room temperature. So everyone knows classical bits in the personal computer. Usually we use the classical bits 0 and 1. But quantum bits, qubits is the superposition of 0, 1. So then if you use a classical bit, calculation takes 12 days. However, if you use a qubit, the calculation takes 60 minutes. Huge progress. So then we must realize quantum computer. So then, as I told you, minimum use for quantum information is the superposition of 0 and 1. So this is available for the quantum computer. So for the quantum computer, the low temperature is okay because now only one quantum computer is working in IBM. They put the quantum computer in the liquid field. So then temperature doesn't matter. However, more recently, this is available for the quantum sensor. So then quantum sensor is to apply biological system. So then for the quantum sensor, room temperature is needed. However, so in both cases, high temperature is preferable. High temperature is good. So then how to create the best qubit is most important. So then rules of Di Vincenzo. So then first, scalable with well-characterized qubits, the ability to initialize the state of the qubit to a simple fiduciary state. Third one is the long relevant coherence times, a universal set of quantum gates, a qubit-specific measurement capability. This part is very important to get a good qubit. So then there are several research for the photons, quantum dots, and the superconducting loops. So IBM uses this superconducting loop and trapped atom and nitrogen vacancy in diamond. However, more recently, molecular magnet is another good candidate for qubit, for the molecular spin qubit. So merit of the molecular magnet is a spin phase controlled by PRCPR, high spin polarization of electron spin, high molecular density. This is a big advantage. However, demerit is a short lifetime of superposition, spin relaxation time. So during the superposition, we must finish the calculation. But if the superposition lifetime is short, the calculation doesn't finish. So then we need a longer lifetime for superposition of T2. So this is a definition of spin relaxation time T2 and spin lattice relaxation time T1. So this everyone knows T1 and T2 very important. But the most important thing is twice T1 is larger than T2. This is the most important for spin qubit. So then spin lattice relaxation time T1 factors influence to T1 is a inner magnetic field, nuclear spin, magnetic dipole interaction. On the other hand, in the spin relaxation time T2, factors influence to T2 is nuclear spin, neighboring spin, and rotation measure. So this is a result of molecular-based magnet. T2 more than 100 microseconds, that is enough for calculation. So some metal compound, vanadium compound shows a longer lifetime, more than 100 microseconds. This is very good. And also, ferrocyanide, also vanadium, room temperature. Also, this is very good. So some metal complexes are good candidate for molecular spin qubit. So then this most investigated compound is a vanadium for one spin system. The square pyramidal, so this is a red one. So validation, relaxation, and blue one is a hexagon sulfur vanadium. So green one is a shorter lifetime. Then we must correlate between magnetic properties and optical properties, especially terahertz region. You can see one compound shows a 2 peak, other compound shows a 1 peak. So this is a intermolecular state mode detected in the terahertz region. We correlate between magnetic properties and optical properties such as a terahertz region. So then this is other compound, oxyvanadium compound 1 and oxyvanadium alkyl compound 2. So this is a magnetic field dependence of relaxation. So this compound has a 2 relaxation time from the RS plot, and this has a 1 relaxation time. You can see the terahertz. So 2 relaxation time compound has a 2 peak in the terahertz. This is a molecular deformation, molecular stretching, and 1 relaxation time compound shows only 1 stretch mode in the terahertz. So we realize relationship between magnetic and optical properties. So magnetic optical properties strongly correlated. So then, as I told you, most investigated compound is the oxyvanadium. So spin is 1, spin quantum number 1/2. One spin system is good candidate for molecular spin qubit. Another example, chromium 5, cobalt 2 low spin, copper 2, nickel 3 low spin, iron 3 low spin. However, so far, most investigations are focused on the oxyvanadium and the copper compound because these are commercially available material or well-known compound. But we focus on all metal ion with spin quantum number 1/2. So then, outline for spin qubit and coherence in my talk. So first one is the crystal engineering method. This is so-called morph spin qubit. I don't like morph. MOV is not science, just teaching, very boring. So then, but I focus on the MOV spin qubit. So to suppress the intermolecular vibration of oxyvanadium TPP by using 3D MOV. So you know, crystal structure of kappa NT in the crystal structure, the planar structure. However, in the vacuum condition, distorted. So then, crystal lattice which suppress the intramolecular vibration, planar distorted. So lattice is very important. Then I focus on the oxyvanadium TPP. Starting material, zero dimensional, soft lattice. We focus on, we put this oxyvanadium put into the MOV, strong lattice, rigid lattice. We compare the soft lattice and three-dimensional strong lattice to make clear the factors of spin behavior influenced by the crystal lattice. So for this purpose, my students inside tetracarboxylase benzyl oxyvanadium TPP, this starting material zero dimensional, put the zinc ion to make a two-dimensional network, to put the bipyridine to make a three-dimensional MOV. I compare the zero-dimensional starting material and the final target three-dimensional MOV. We compare the crystal lattice. So this is a crystal structure, vanadium distance. This is starting material zero-dimensional. This is three-dimensional MOV. So vanadium distance is different. However, we measure the EPR spectrum. This diluted in the titanium oxide non-magnetic molecule. Then this is three-dimensional MOV, zero-dimensional. So you can see this G parallel and the perpendicular. So from the EPR, G value is same between 3D MOV and the zero-dimensional starting material. This means the same electron structure. So then we measure the terahertz. Zero-dimensional material, we observe the sharp peak on the 67 wavelength. This is the deformation of the molecule and also stretch mode of the metal ligand. However, in the three-dimensional mode, no peak because that is rigid. Deformation is suppressed. Stretch mode is suppressed. So then we success to suppress the lower energy of the deformation of the three-dimensional mode. So then this theoretical calculation, some deformation of the zero-dimensional molecule around here. This is observed in the terahertz region. So then this result. So relaxation time. So three-dimensional mode, we observe the coherence even at room temperature. And also Rabi nutation. We do the pulse pair, we detect the echo. Usually Rabi nutation observes a very low temperature, liquid nitrogen, liquid helium temperature. But in our case, even at room temperature, we observe the very beautiful Rabi nutation due to the strong lattice. So then, in the case of 3D MOV complex, Rabi nutation or coherence was observed due to the rigid lattice. So, lattice is very important. So then, I focus on the kappa compound. You know, kappa compound shows usually antiferromagnetic interaction between the kappa-kappa ion. But only one kappa ion isolated, doping into one-dimensional, two-dimensional, three-dimensional material, doping to isolate one kappa ion. So one kappa ion should show the slow magnetic relaxation. So for example, so this is a platinum 2 mixed phase compound, zero-dimensional starting material, one-dimensional with counter percolate. This is a one-dimensional lattice, and this is a counter hydrogen instead of percolate. Two-dimensional network. Lattice is zero-dimensional, one-dimensional, two-dimensional, and platinum 4, platinum 2, platinum 4, platinum 2. Mixed phase compound, very famous compound. This is a diamagnetic species. So then we put doping kappa 2 instead of platinum 5%. Isolate the kappa ion. So one-dimensional compound shows a slow magnetic relaxation. Two-dimensional shows a slow magnetic relaxation. This is due to the one kappa ion shows a slow magnetic relaxation. Work as a molecular spin tube. So then two-dimensional is longer lifetime compared to one-dimensional due to the rigid lattice. And we dope to the three-dimensional MOV. I don't like a MOV, but I use a MOV. So in the zinc morph, this diamagnetic species, we doped 5% of copper in the zinc. So powder pattern is same structure. So successfully copper 5% doped. So this magnetic dependency, very beautiful frequency dependency, slow magnetic relaxation. One copper ion shows a slow magnetic relaxation and temperature dependency, slow magnetic relaxation observed. This due to the phonon bottleneck effect. So from the RS port, so this slow magnetic relaxation due to the phonon bottleneck effect. So then we switch to the Prussian blue analog. So hexacyano cobalt is a low spin diamagnetic, but iron 3 is a paramagnet. So iron 3 has a 1 ampere electron on the DX3 orbital. I dope iron to diamagnetic cobalt. So very beautiful frequency difference observed. Iron 1 atom shows a slow magnetic relaxation. One spin shows a slow magnetic relaxation. This is available for the molecular spin qubit, and the relaxation mechanism is the phonon bottleneck effect and the Raman process. So let's move to the G-tensor engineering method. Relationship between isotropy of G values and the T1 in oxyvanadium TPP and chromium nitride TPP. So original G-tensor engineering means the multi-bit system by using isotropy of G values and space arrangement developed by Richard Penny in Manchester. But we use the electrospin will be influenced by the vibration. If G values have highly isotropy, then I focus on oxyvanadium TPP spin number 1 spin and the chromium nitride 1 spin. Both has 1 spin to make clear the influence of isotropy of G value to T1. So this is a crystal structure. So from the square planar, so chromium and also vanadium are distorted. So this is an EPR spectrum. You can see chromium nitride, G isotropy is 0.0398, but oxyvanadium isotropy 0.0235. So oxyvanadium is smaller isotropy of G value. So then this is a result, relaxation time. Chromium nitride shows a faster relaxation time. On the other hand, oxyvanadium shows a longer lifetime because smaller G isotropy of oxyvanadium. So both compounds show a slow magnetic relaxation. This is not sigmoidal magnet, but a phonon bottleneck effect. And oxyvanadium better than chromium nitride due to the smaller G value. So third one is the orbital engineering method, relationship between different occupied orbital or NIC3 compound. Generally, NIC3 compound are unstable, but macrocyclic ligand stabilize NIC3, and axial ligand NO3, counter NO3. This is abbreviated NIC NO3. Actually, chloride, counter purple. This is abbreviated NIC chloride. You can see bulk NIC chloride shows an antiferromagnet due to the NIC antiferromagnetic interaction. However, diluted in the diamagnetic cobalt, we isolated NIC3 one atom. So both NIC3 compounds show ampere electron located in G square orbital because of the halo. So both compounds show the slow magnetic relaxation. This is not sigmoidal magnet, but a phonon bottleneck effect. So this is a result. Red one is a NIC NO3. Blue one is a NIC chloride. NIC NO3 is longer, NIC chloride is shorter because chloride has a nuclear spin. So then nuclear spin disturb, then the coherence, then NIC chloride is shorter lifetime. But NO3 oxygen coordinate to NIC, then oxygen has no isotropies, then longer lifetime. So then NIC NO3 is longer lifetime. So we switch to the NIC MNT. So bulk NIC MNT shows a antiferromagnetic interaction or spin pulse interaction between NIC. However, we dope the gold. So we isolate NIC3 ion by doping the diamagnetic gold. So then ampere electron is occupied DX3 orbital because this is a square pyramid. So consistent with the experiment data and theoretical calculation. So This shows a slow magnetic relaxation. So these are all data. This is a nickel MLT. So nickel MLT is strong lattice and deformation, molecular deformation, then shortest lifetime. And nickel NO3 is the longest, and nickel chloride second. So from these results, nickel 3 is also good candidate for the molecular spin qubit, but the nickel NO3 is best. So finally, molecular technology method usually use a molecular design. Molecular design means that you think about some physical property by molecular design. But molecular technology is strongly connected to the real application. So we usually use a molecular technology method. Relationship of T1 spin lattice transition time between oxyvanadium and oxyvanadium annulen. We switch from the TPP to the annulen, new macrocycle. So this is already reported result. Compound 1 here, compound 2 here, oxyvanadium here, and the phthalocyanine here. So we switch from this macrocycle to the annulen macrocycle with propyl and hexyl to make clear the influence of ligand symmetry on T1. So this hexyl, so bridged by hexyl, this macrocycles are rebanded, and this is a propyl disorder. So we compare these materials. So this crystal structure, metal-metal distance, hexyl, propyl, and oxyvanadium. So unfortunately, propyl has a disorder. Then EPR spectrum very complicated, but the hexyl is simulated. So in the hexyl, G isotropy 0.02, oxyvanadium 0.023. So hexyl is smaller G isotropy, then you can say this is oxyvanadium. Hexyl is smaller G value, then longer lifetime. Surprisingly, propyl is the longest lifetime, all materials. So both compounds show the frequency dependency. Actually, this is not single magnet, but the photon-bottleneck effect. So then, surprisingly, propyl is the longest lifetime. We need a molecular technology by using theory. So, in the first part, I focus on 4 approach to realize molecular spin qubit. So second, high-density memory devices. First one is single molecule memory performance by single molecule magnet, metafluorine single molecule magnet, encapsulated into single carbon nanotube, metallic conducting single molecule magnet with negative molecular resistance, photoswitchable single molecule magnet. Every day, every time, you use a classical magnet. But I use a single molecule magnet. Why? Why should we use single molecule magnet instead of classical magnet? To overcome Moore's limitation. Human being faced with the Moore's limitation. You must overcome Moore's limitation. You know, Moore's limitation, Moore's law. Every 1.5 years, memory capacity increased twice according to the Moore's law. Now 2, 3, around here. So, in order to increase the magnetic ability, we must make the classical magnets smaller into nano size. However, classical magnet does not work in the nano size, just in the nano size, quantum fluctuation. Then we must use the nano size magnets, such as single molecule magnets, such as double cathode terbium. These material to overcome the Moore's limitation. That's why I use a single molecule magnet every time. So everybody knows the single molecule magnet. Classical magnet is 3-dimensional ordering. So 3-dimensional ferro or ferrite, 3-dimensional magnetic ordering. However, single molecule magnet is a 0-dimensional. So this composed of mono or multinuclear nanocluster metal complex. This molecule and other molecule, no interaction, isolated. And this has a double potential below blocking temperature, upstream or downstream, freeze. So under the magnetization, upstream graduated to the downstream. In this occasion, we observe the C stages. So one molecule works as one magnet, works as one memory. Then this is available for high density memory devices and also quantum computer. So then this is other view. This is a potential barrier below blocking temperature, upstream or downstream flows. and this is thermal relaxation and quantum noise and quantum tunneling occurs. So this is thermal relaxation, hysteresis, and you can see the step. This is the quantum tunneling. So this is available for the memory devices and the quantum computer. So frequency dependency in AC susceptibility. In the classical magnet, three-dimensional magnet, we shift from 1 Hz to 1000 Hz, no frequency dependency. However, Qubits magnet, zero-dimensional, very beautiful frequency dependency of that, perfectly defined. And also, heat capacity is powerful method to detect the ordering. So in the three-dimensional antimatter magnet, at the needle point, three-dimensional ordering occurs. Then at this needle point, very sharp peaks of that. This is three-dimensional ordering. However, Qubits magnet is zero-dimensional, so no peak. So perfectly defined between classical magnet and Qubits magnet. So then, as I said, in order to overcome the Moore's limitation, we must use the Qubits magnet such as double capital signing. So our final target is Japan National Library has 20 million books. All information are stored in the sugar cubic size memory devices. So then another important point is the spin choice. Last century is the electrons age. Electrons is based on the freedom of charge of the electron, but the spin choice is based on the freedom of charge and spin. So spin choice is much advantage compared to the electrons. For the M-RAM, advantage of spin choice is no volatility of information, high operation speed of nanosecond, high information density, low consuming electric power. This is a big advantage compared to electrons. So several spintronics, so-called magnetic resistance. Typical one is a giant magnetic resistance, tandem magnetic resistance. Every day you use a GMR, TMR in your personal computer, and CMR, BMR, EMR. So let me show you example. Giant magnetic resistance, 1988, Gilbert discovered. They got a Nobel Prize. This is a classical magnet, non-magnet, classical magnet. Spin is antiparallel, low conductance, division 0. Spin is parallel, high conductance, division 1. 0, 1, 0, 1 switch in the classical magnet. However, to overcome the Moore's law, we must use a Qubits magnet instead of classical magnet. Every time we use a Qubits magnet to overcome the Moore's limitation instead of classical magnet, so then we usually use the scanning tunnel microscopy STM. This is an instrument for imaging service at the atomic level and also scanning tunnel spectroscopy STS. This provides information about the density of state. So DIDV, the tunnel conductance, DIDV is directly proportional to the sample dose. We usually use this STM and STS at very low temperature. So then first topic is the single molecule memory performance by single molecule magnet. Every time we use a single molecule magnet to overcome the Moore's limitation. So for this purpose, we use a tunnel magnetic resistance. In the hard disk head, spin is parallel, high conductance, division of 1. Spin is antiparallel, low conductance, division of 0. But this is a classical magnet. Instead of the classical magnet, we use a single molecule magnet to overcome the Moore's limitation. So how to write and read one memory in single molecule magnet? So STM chips is electrode 1. Single molecule magnet is electrode 2. We use this TMR how to write and read one memory in single molecule magnet. So as I told you, by using the tunnel magnetic resistance, spin of the chips, spin of the single molecule magnet parallel, high conductance, division 1. Spin of the chip, spin of the single molecule magnet, antiparallel, low conductance, division 0. 1, 0, 1, 0 switching by using the single molecule magnet to overcome the Moore's limitation. So you must distinguish now spin up or spin down, 0 or 1, okay? But then we must visualize magnet by tunnel magnetic resistance. Spin of the chip and the spin of the single magnet down, division is 0. So in this case, spin color is dark, up spin color is bright. Down spin is dark color, up spin is bright color. So depending on the direction, spin color change. Then you must believe. Now spin color is bright, then spin up. Now spin color is dark, now spin down. So then, for this purpose, we get the spin polarization chips. You usually gradually use chips. One cobalt is ferromagnet. One cobalt atom is paramagnet. We put the plasma using chip, LCN chips to the bulk cobalt. Take off one cobalt atom. One cobalt atom is a paramagnet. So we use a plasma using one cobalt atom. So this is a result to check the ability of memory effecting classical magnet. This is a cobalt ion, classical magnet. You can see bright spot, spins up. Division 1, 1, 1, 1. This is a dark color, down. 1, 1, 1, 0, 0, 0, 0, 1, 0, 1. We put the information 1, 0 in the bulk magnet, like oscillator again. Black, down spin, white, up spin, like oscillator. So I show the movie. Okay. Now we shift the external field. Now spin will shift down. You can see now 0, 0, spin hips. Now spin up, 1. Now spin 1. We put the information 1 or 0 by shifting the external field. So we realize memory device, but this is a classical number. Classical number. 1, 0, 1, 0. So put the information. So this means that from the beginning, down, 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 up, like this. Up, down, down, down. So large stresses due to the timeline. So then finally, I realized by using the spin multi-magnet, we put the information upspin, downspin in the one spin multi-magnet. We must realize. So then for this part, this is a spin multi-magnet. Now 2.5 Tesla here. So now dark color, spin down. So we see the external magnetic field. Yeah. So now 2.5. Now dark color, spin down, 0. Now color change. So color change. Now bright, spin up. Now color change, spin down. We put the information into one molecule, 0, 1, 0, 1. We realize spin multi-memory devices. Again, I show this experiment is very difficult and very low temperature. So now 2.5 Tesla spins down, dark color, 0 dimension 0. Now color change, so spin up, now division 1. Now down 0. We realize spin multi-memory devices. So unfortunately, this is Japan, but we can make a monolayer of the double copter signing and using the multi-spin polarized system. So we see the sheet, put the information. We see data information. We realize spin multi-memory devices. So let's move to the metal fluorine spin multi-magnet encapsulated in single carbon nanotube showing the giant amount of resistance. Every day I use a spin multi-magnet instead of classical magnet to overcome the Moore's limitation. So single carbon nanotube 80% semiconductor, 30% metallic. We inserted in the spin multi-magnet conduction electron and local spin multi-magnet interact to show the negative magnetic resistance. For this purpose, we usually use a disposition one metal fluorine spin multi-magnet and also double copter sign. We inserted. So this is a motif pivot. So very easy. High vacuum and high temperature and a few days and wash outside. So this is a time image. This is a motif. You can see metal fluorine inserted. So in the EDX, disposition scanning actually inserted. So this is a hard stain. So disposition with the white broad spot is a disposition, one-dimensional align. So Raman spectra is powerful to detect the interaction between single carbon nanotube and the metal fluorine. So then before, after, rate shift, Raman spectra is observed. Rate shift means charge transfer occurs from metal fluorine to the single carbon nanotube. So metal fluorine and single carbon nanotube interact by the Raman spectrum. And the interest point is coercivity. Before encapsulation, coercivity is 0.5. After encapsulation, coercivity increase 4 kilo. One motor increase. So this quantum tunnel is suppressed. So sigmoid magnet behavior improve. So another example, double capital sign terbium, we inserted in the single carbon nanotube. So this, yes, in this case, we use a solution method. So a few days and push outside. So you can see this motif, double capital sign is stacking in the one dimension. So in the EDX, actually terbium is included. So I want this Java, but you can take one carbon nanotube, put the electrode by using the lithography. So then we measure the magnetic resistance. So this is one carbon nanotube. This is a gold electrode, but no magnetic resistance. We switch from gold to nickel. You can see very small, but 0.37% negative magnetic resistance observed. This is due to the conduction electron and localized single magnet interact. So then we realize negative magnetic resistance and also Coulomb blockade oscillation. So this is a carbon nanotube. This is a palladium electron. We get this device by the lithography. So then before encapsulation, after encapsulation, we compare the Coulomb blockade. So then before encapsulation, very beautiful oscillation observed. And we switch the external field. Carbon, single carbon nanotube doesn't change because no spin in the before encapsulation. But after encapsulation, so they're very noisy because conduction electron and localized spin interact, spin flip occurs. So then red one is Coulomb blockade after encapsulation. And also, what is the external field? Red color change to blue color. So magnetic field effect is observed. Actually, we observe the interaction between conduction electron and localized sigmoid magnet. So let's put the metallic conductive sigmoid magnet with negative magnetic resistance. We usually use a sigmoid magnet to overcome the Moore's limitation. So many organic conductors, and we use a sigmoid magnet. Conduction electron, localized sigmoid magnet interact to show the giant magnetic resistance, negative magnetic resistance. For this purpose, we usually use a beton. This shows the superconductivity or metallic behavior, and also accelerator is a cobalt single ion magnet. We compare, we put in both and by electrochemical method, we obtain the conductive sigmoid magnet. So this beta double prime BO3 and cobalt PDMS to this material. So beta double prime bedo is this kind of stacking. So this is a crystal structure. This is organic bedo. This is a single ion magnet. So segregated two-dimensional stackings is observed. So from the Raman spectrum, 0.77. So partial charge transfer occurs from the donor to acceptor. So this is the evidence for conducting sigmoid magnet. Then we measure His. Actually, this compound shows His below 5 Kelvin. So this conducting sigmoid magnet and also frequency dependency observed. Actually, this is the evidence of sigmoid magnet. And we measure the conductivity. This shows the metallic behavior. But 3.5 Kelvin metallic initiator occur. But we increase the pressure. So conductivity increase 1000 G. So this shows a negative magnetic resistance by the metallic conduction and localized magnetic interact to the negative magnetic resistance. So every time we observe the negative magnetic resistance, so this is a band calculation. Actually, film level is cutting, so this is actual metallic. So then we must realize giant magnetic resistance. So then we use a spin barrel, cobalt substrate, single magnet, chromium tips. So DIDP 0 Tesla, 5, 1 Tesla, 10, twice. This means that 200%. Finally, we realize giant amount of resistance. Finally. So let's use the photo-switchable single magnet. This is a famous photo-switchable molecules. This carbon gas, this carbon coordinated single magnet. In the carbon compound created high concentration, but the visual radiation. This carbon destroyed. No pi conjugation. Closed type, open type, reversible switchable. So if bridge open type, no interaction, then single magnet. But UV radiation interaction occurs, then classical magnet. Single magnet, classical magnet, switchable more than 1,000 times. So open type, no pi conjugation, colorless. By UV radiation, carbon created high conjugation, so then color. And visible radiation, open, non-color. Switchable more than 1,000 times. So in this purpose, I use this ligand and also single magnet. So this is a closed type. This single magnet, this single magnet connected. So then this is a classical magnet, bulk magnet. But visible radiation, this carbon is destroyed. Then this is no interaction. Then this is the single magnet. Classical magnet, single magnet, classical magnet, single switchable by visible UV radiation. So this is a UV visible spectra. First close classical magnet, visible radiation open type, red color, and again UV return to the first one. Reversible, switchable also UV visible spectra, and also open type single magnet shows the cold port. This is actually evidence of single magnet. And the interest point is the open type single magnet. In the AC suspect high double prime imaginary part shows a peak. Then this is the evidence of single magnet. And UV radiation interaction occurs, then bulk magnet, no high double prime. But again, UV visible radiation open type. Single magnet, classical magnet, single magnet, classical magnet, switchable more than 1,000 times. So we realize switchable between classical magnet and single magnet, UV visible radiation 1,000 times. So as I told you, every time we use a single magnet to overcome the Moore's limitation. So but the important thing is how to increase the hysteresis temperature. Now, highest hysteresis temperature 80 Kelvin. Richard Bayfield in Sussex University. He has a champion record, 80 Kelvin. But we must increase the hysteresis temperature around room temperature. So, two important things: to increase the energy gap between the ground state and the first subvector, and to suppress the quantum tunneling mechanism QTM in the ground. Both are very important to increase the hysteresis temperature. So, if the potential barrier is very high, but quantum tunneling occurs at the ground state, hysteresis temperature is very low. So we must suppress the quantum tunneling at the ground state. So then for this purpose, I focus on double decapitating our compound, suppress the QTM. So for this purpose, ideal square antiprism and exchange bias for ground state, both are very important. So for upper after sign, lower after sign, no distortion, square period D4H. In this case, ligand field includes the B44 and B64. This B44, B64 is exact source of quantum tunneling mechanism. But upper after sign, lower sign, 45-degree distortion, D4D. So ligand field disappear, D44, D46. So square antiprism suppress the quantum tunneling. And also exchange bias, diamond model. George Bristow and Wolfram reported in the single magnet has a diamond as a 0 Tesla, no step, suppress the quantum tunneling as a ground state. So, as a ground state, two spin at the same time, flip two spin. This possibility is very low. Then we can suppress the quantum tunneling at the ground state. So this is so-called exchange bias. For this purpose, my student, since I double capital sign is bridged by the Benjamin. This shows the ferromagnetic dipole interaction. This shows the hysteresis around 25 Kelvin. Starting material shows the less than 5 Kelvin. But this commercial type is 25 Kelvin, and other students inside double fuse type. So heated temperature 27 Kelvin, and finally my students inside degree crystal. So heated temperature 31 Kelvin. So heated temperature increased by using the exchange bias and anti-collision. So, and 3 years ago, I got a Chemical Society of Japan award. So I published my review article, more than 50 pages. So you can see my research history from this review article. So, but finally, I stress, what is science? What is science? To create new concept, of course. New compound, new physical properties, new reactions, new theories, new measurement. But everybody does every day these things. This is not science. Most important thing for science is to create a new research field. It takes 30, 40 years. For the student, you have only one chance for your life. So then my field, multifunctional nanoscience or advanced metal complexes. So multifunction between magnetism, optics, conductivity, but many research work on the multifunction. But I focus on the nanoscience and also metal complexes. I focus on the nanoscience. Nanoscience means that quantum effect and non-linear. Today I focus on the quantum effect and metal complexes. This is my field. It took 30, 40 years. So science should be not number one. Number one is overcoming other researchers. Number one becomes number two, number three, number 10. Nobody remember number 10. But only one. If you forget the only one, but you can check the text. Only one is cited in the text. So science should be only one. So science should be not from 1 to 100, but from nothing to 1. From 1 to 100, this is just development of other researchers' work, no originality. But from nothing to 1, this is actually pioneering to create a new research field. So science should be from nothing to 1. So important for science is originality or creativity, and the most important thing is to enjoy science. So in Japan, the average age in Japanese professor is around 90 years old. 90 years old. Okay, in Japan. But usually we sleep 8 hours. You sleep 8 hours every day. 8 hours means that one day is 24 hours. 1/3 you are sleeping. That means that totally 90 years old. You sleep for 30 years. You sleep for 30 years. Too much sleeping. 3 years is enough. Once a week, you must sleep. For me, when I was a graduate student, I sleep a few hours every 2 days. I stay in the lab. No sleeping, no eating. You must focus on the research. So then, for the natural science, already cleared only 5 to 10%, but uncleared more than 90%. Unfortunately, you focus on the already cleared field very important. You must challenge to uncleared field. So it takes 30, 40 years. So what is science? As I told you, to create new research field, it will take 30, 40 years. For the young student, you have only one chance for your only one life. So finally, I acknowledge my many co-workers. Professor Komeda is a specialist of the STEM states. Professor Kato is all materials, and Emeritus still work on the molecular spin qubits and some theoretical calculation in Java group and devices and also conducting material. And more than 10 years ago, my lab was more than 55 members. Some are missing, but many foreign students and Dr. Lee, China. China, or it's that in the audience, more than 10 years ago, he was my student. After that, he moved here. So, and Egypt, India, Egypt, and Bangladesh, and China, France. So, more than 55 members have foreigner, common language, English in my lab. But I don't remember the name of my student, unfortunately. Thank you for your kind attention. Thank you.
Thank you very much, Masahiro, for a whirlwind of the talk. Amazing. So, do you have any questions? Oh, yes, many questions.
Yes.
Max, okay.
Earlier on when you were talking about your thinking, this was the nuclear complex.
Yeah.
You showed the MNT and the 9
Yeah.
and the chloride.
Yeah.
With these sorts of complexes, often the anion, the cobalt with the anion, occupies the same matter site and he interacts coulombically.
Yeah.
So in that case, is it the bonding that's important, or is it the distance between the anion and the metal center?
Yeah, and at this, good question. At this stage, we see many different cation and anion type, and because cation exchange many compounds. So, but for this part, we focus on one compound, one is tetrabutyl ammonium. So we switch to other cation, so different behavior. So totally, we must evaluate. Yeah.
Is the goal not to get rid of the transfer entirely?
Yeah.
Thanks for the very nice stuff. So in your spin phonics one, in the GMR, you showed the switching. These are the magnetic fields required around the other Teslas, right? So any strategies to scale them down to millitesla?
Yes. Every time I was asked, because for the spin free, strong magnetic field, 1 Tesla, 2 Tesla, so unbeatable. So then for the real application, very hard. Yeah, that's a big problem. Good question.
And another quick question is, there's a lot of work going on in anti-ferromagnetic spin. Do you have any plans to work?
At this stage, I don't think. In the first part, I focus on the isolate one spin system, because due to the anti-ferromagnetic interaction, we can not observe the spin in the first part. And also for the something more demand show the intra-ion anti-ferromagnetic interaction, but in our case, almost focus on the double capital science and kind of material. So then, at least I don't think the anti-ferromagnetic interaction.
Thank you.
Actually, with regards to the single molecule pattern,
Yeah.
You said that there shouldn't be interaction. So I was just wondering what kind of spatial density you expect to be able to get out of the device to be. I was wondering what kind of density of single molecule magnets you can have, or how close together could they be before they start interacting?
Between surface and the molecule.
Or between themselves? Like,
Oh, isolate.
Yeah, they have to be isolated. So how close can you bring them?
That's a good question.
Exchange interaction.
Yeah. And almost ignore, because in our case we sublimate it. Then we isolate the molecule and sometimes closing, okay? And we realize the mono area of that's a close packing. Even so, no interaction. No interaction.
Okay. Wonderful. I'm afraid we're going to have to, because there is a lecture here afterwards, so we have to finish, unfortunately.
Okay.
But we can carry on. You're available for discussions this afternoon, so at least some time in materials and in physics later on, we can organise further sessions. So thank you so much for the amazing presentation.
Thank you.
Very thorough. yeah, sorry, we're just back here for